Alright, here's the binomial theorem. This is a special case of something called the multinomial theorem, which we probably won't need in this class, but nonetheless it's very, very useful and pops up in probability. If you studied probability theory before at all, you've probably encountered the binomial random variable. So this formula should look very familiar. For real numbers a and b and a non-negative integer n, it turns out you can express the sum of a and b raised to the nth power as this sum right here. The sum from k equals 0 up to n of n choose k. Okay, so this is that n choose k coefficient. Also called, sometimes this is called the binomial coefficient, because they're the coefficients in the binomial expansion of this guy. Okay, a to the k, b to the n minus k. Okay, so just for a little example, so that you see that this actually works. Suppose that a equals 6, say, and b equals, I don't know, like -2, and maybe n equals 3. Okay, then the left-hand side there is like this. This is the left. This is the right. Right. This is the left-hand side, right-hand side, like that. So the left-hand side then becomes 6 plus -2 raised to the third power. Of course, 6 plus -2 is 4. 4 to the third is 64. Okay. The right-hand side then is, let's see, first term, k equals 0 and n is 3. Okay. This k starts with 0, n is 3. We choose 0 times a is 6 raised to the k is 0 in the first term. B is -2, raising that to the, let's see, 3 minus 0. Okay, for the second term I get 3, choose 1, times 6 to the first, times -2 to the 3 minus 1. And then for the third term, I'm going to have, 3 choose 2 times 6 to the second, times -2 to the 3 minus 2. And for the last term, finally, I have 3 choose 3 times 6 to the third times -2 to the 3 minus 3. Okay, now let's simplify this a little bit. So, of course, I can work this out using the formula for 3 choose 0 with the factorials and all that stuff, but if there's simple numbers like this, I don't really have to do that. I know that there's only one way to choose no things from 3 things. Okay, there's only one way to do nothing when you have several things to do. Right? You just sit there and do nothing. Actually, that's not true. I figured out all kinds of ways to do nothing, but that's another story. 6 raised to the 0th power, of course, is 1. That's this. This is that. Right? -2 to the 3 minus 0. This is -2 to the third, right? Which is -8. And then 3 choose 1. How many ways, if I have 3 things, how many ways can I choose one thing from the 3 things? 1, 2, 3. There are 3 different ways to do that, right? 6 to the first is 6. -2 to the, let's see, 3 minus 1 is 2. This is -2 to the 2th, right? Ends up 4. Plus 3 choose 2. How many ways can I choose 2 things from 3 things? Look, 1, 2, 3. There are 3 subsets of size 2 in a set of 3 things. Also, guess what? Another way to know that is that n choose k is always equal to n choose n minus k. That's because, think of it like this, if you have n things, and you're going to choose k of those things for yourself and leave the rest, the n minus k of them, behind for your friend, well, so every choice of k items leaves behind a very specific set of n minus k things. So the number of ways to choose k things from n things is the same as the number of ways to choose n minus k things from n things. Alright, so we're on this third term here, so this 3 choose 2 has to be the same as 3 choose 1 is my point there, which is 3. 6 squared is 36. times, let's see, negative 2 to the first is negative 2. And finally we get 3 choose 3 is 1. 6 to the third is it 216? And negative 2 to the 0, this is just 1. Okay. Alright, so all this becomes negative 8 plus 72 plus negative 216 plus positive 216, and of course this is 64, just like we got up here. They're the same. Okay, so this indeed works. Now, of course, why in the world would you want to do this when this is so much simpler, right? You just take 6 plus negative 2 and raise it to the third power and you get your answer. Well, the answer is you would never want to apply the binomial theorem in a case like this. Where it really comes in useful is when A and B are, say, not known quantities and you want to prove something. Okay, it comes into, it's really useful when A and B are not known.